Welcome to a lesson on changing the order of integration using triple integrals. Here we want to express the triple integral for the volume bounded by 4z equals x squared plus y squared and z equals 4. We want to express the triple integral using the following three orders of integration. The first thing we should remember is that we can determine the volume of a solid region using a triple integral evaluated over the three-dimensional region V integrated with respect to V. And then we replace differential V with our different orders of integration with respect to x, y, and z. Before we start, let's go ahead and take a look at this in three dimensions. So we're trying to determine the volume bounded by this blue paraboloid and this yellow plane. So we're trying to determine the volume of the region in here. A couple of things I want to point out. First, notice that the volume is symmetrical in the first four octants. So what we can do is determine the volume in the first octant and then multiply that by 4. So we're going to go ahead and do that. The last thing I want to mention is that the xy trace, which would be where z is equal to 0, would only have one point at the origin. So instead of determining the xy trace, we're going to determine the z equals 4 trace, or the slice cut by this yellow plane, and you can see it's going to be a circle centered at 0, 0. So what we're going to do now is determine the xy trace, xz trace, and yz trace, and then we'll determine the limits of integration for these three orders of integration. So as I just mentioned, for the xy trace, instead of letting z equal to 0, we'll let z equal 4. Then looking at this equation here, we would have 16 equals x squared plus y squared. So we have a circle centered at 0, 0 with a radius of 4. For the xz trace, we'll set y equal to 0. So we'd have 4z equals x squared. We could solve this for z. We'd have z equals x squared over 4. So if this is the x-axis and this is the z-axis, we have this parabola that opens up. We also know that z is equal to 4. And then for the yz trace, we set x equal to 0. So we'd have 4z equals y squared. And then solving for z, we'd have z equals y squared divided by 4. Again, we have this parabola here in blue that opens up. And we also know that z is equal to 4. So we're calling this the y-axis and this the z-axis. So because we're going to determine the volume in the first octant and then multiply by 4, we're only concerned about the regions in the first quadrant. So here, here, and here. So let's go ahead and set up this first triple integral, integrating with respect to z, y, and then x. Remember, we're going to determine the volume in the first octant and then multiply by 4. The limits of integration with respect to z must be expressed in terms of y and x. Well, the values of z are bounded by this paraboloid and z equals 4. So if we solve this for z, we would have x squared plus y squared divided by 4. That'll be our lower limit of integration for z. And the upper limit of integration will be z equals 4. And now we need to express y as a function of x. Let's go and take a look at the xy trace. Well, y would start at 0 and then go up to the circle. So if we solve this equation here for y, we would subtract x squared on both sides and then take the square root. So the limits of integration for y would be from 0 all the way to the square root of 16 minus x squared. And then for x, we can look at either the xy trace or the xz trace. X starts at 0 and goes out to 4 here, as well as here. So here's the first triple integral, integrating with respect to z, and then y, and then x. Now let's consider the order of integration dy, dx, dz. So the limits of integration for y must be expressed as a function of x and z. Looking at the yz trace, we can see that y starts at 0 and goes out to this parabola, which is a piece of the 4z equals x squared plus y squared. And since we have to express y as a function of x and z, we can start y at 0, but we do have to use this equation up here to express y as a function of x and z. So to solve this for y, we would subtract x squared on both sides, and then take the square root of both sides. So the upper limit for y would be the square root 4z minus x squared. And now for the limits of integration for x, which must be expressed as a function of z, we'll look at the xz trace as we see here. So x starts at 0 and then goes out to this parabola, and the equation of the parabola is 4z equals x squared. So to express this as a function of z, we'll have to solve this equation for x. So if we square root both sides of this equation, we would have x equals the square root of 4z, or 2 square root z. So x starts at 0 and it goes up to 2 square root z. And then for z, we can see from the xz and the yz trace, the lower limit would be 0 and the upper limit would be 4 here and here. Now let's take a look at the order of dx, dz, dy. So the limits of integration for x must be expressed as a function of y and z. Looking at these two traces here, we can see that x starts at 0 and goes out to the curve, and these curves are a slice of the paraboloid, so x will go from 0 all the way to this equation here, solve for x. So we'll have the square root of 4z minus y squared. And then for the limits of z expressed as a function of y, we'll look at the yz trace, which is here. So z starts on this curve here and goes up to 4. So the upper limit will be 4, and the lower limit will be the equation of this graph expressed as a function of y. So if we solve this equation for z, we would divide both sides by 4, we'd have y squared over 4. And then for the limits of integration for y, we can see from both the xy trace and the yz trace that y starts at 0 and goes up to 4 here as well as here. So now we've completed 3 different triple integrals that would represent the same volume of that 3-dimensional region. And just so we can see them all together, here they are. You may want to try working some of these out to see if you get the same answer, but I believe this middle one becomes very challenging to integrate. And so often it is helpful to think about the order of integration when setting up a triple integral, because it will affect how difficult it is to integrate. I hope you found this helpful.